I'm Joel Primack. I'm the chair of this session. This is one of 5 sessions at this APS meeting organized and sponsored by the Forum on Physics and Society. I was one of the founders of the Forum on Physics and Society in the early 1970s, and I chaired it a couple of times. So there are 3 talks in the session. The first one by Steve Chesley, which is about to start, is about detecting Earth-crossing asteroids that could possibly be a danger. The second one by Brent Barbie is on planetary defense, basically protecting us once we've discovered that there's a problem. And the third is also on protecting, but possibly involving the use of nuclear weapons. And that's by David Kaplow. So Steve Chesley is at Jet Propulsion Labs, and he's been working on these kinds of issues for, I think, his whole career at JPL. So let's welcome him, and he has about 30 minutes to give his talk on this. And then there'll be time for questions.
Thank you. Can you hear me okay with this mic? Okay, thanks. Yes, my name's Steve Chesley. I work at NASA's Jet Propulsion Laboratory. And one of my main jobs is to make sure that we don't get hit by surprise by an asteroid. So if it's in your job description to warn and prevent against asteroid impacts, there's 3 things you have to remember. The first one is to find them early. And the other 2 don't matter very much, okay? So I want to just point out a couple of things on this title slide. What you have here on the left is an asteroid about a little less than a meter across probably that entered over southern Ontario last November. So think about the rock the size of your chair coming in and making a spectacular fireball. We actually announced this 20 minutes after it was discovered, while it was still 3 hours out into space. And that allowed for 3 hours of characterization, tracking, and all kinds of scientific observations. Sort of a different case, this is Meteor Crater in northern Arizona. This was 50,000 years ago, roughly, 50-meter nickel-iron asteroid produced about 10 megatons of energy in TNT. So this is the kind of thing that would sort of ruin a state or a European-sized country if it happens to hit. These are hitting all the time, and these are fireballs reported by US government sensors. Nobody tells us exactly what that means, but I think it's probably pretty obvious. These are down-looking satellites looking for energy releases in the atmosphere or on the ground. They're not looking for natural energy releases, but they see a lot of fireballs entering the atmosphere. I call your attention here to, and this is an interactive chart. You can go to our website and click on any one and get the details. These folks are not known for oversharing information. They don't give us any error bars on their information. They don't tell us how complete the data set is, but there's still clearly a lot of things they're hitting. I'll call your attention to this red one here, which is Chelyabinsk, Russia. About 10 years ago now, this thing is a 20-meter asteroid. It exploded over near the city of Chelyabinsk, half a megaton of energy, in this case released high up in the atmosphere, and it broke most of the windows in the city of about 1 million people in February in Russia. This is not the ideal time to have all your windows broken. Hundreds of injuries were reported, both for flash blindness and flying broken glass, because we're all humans and our tendency is to rush to the window and see what's going on out there. Well, in this particular case, that's a really bad combination, because not only do you get the flash, but you also are facing picking glass out of your face for a while afterwards. Okay, the obligatory Earth in a cosmic shooting gallery depiction of these are the potential hazardous asteroids that we're worried about and we are tracking and paying attention to. For our good luck, In a sense, these are all the orbits, but the asteroids are not on all points in their orbit all of the time. So this looks sort of a lot worse than it maybe really is. And yet, I think the takeaway is that space is big, but not that big is the point. So a little bit of terminology. NEOs are what we refer to as near-Earth objects. These are anything that comes within a 1.3 astronomical unit sphere from the sun. The Earth is by definition on this 1 astronomical, 1 AU orbit, and anything that comes within 1.3 AU, be it a comet or an asteroid, we call that an NEO. If it's an asteroid, then we say it's a near-Earth asteroid or an NEA. There aren't that many comets in this group, so sometimes we're a little cavalier and we just interchange NEO and NEA, but that's the precise definition. Also, these NEOs don't necessarily come anywhere near the Earth, but there are a group we call potentially hazardous asteroids that their orbit brings them close to the orbit of the Earth. In particular, you can think of a torus of radius 0.05 AU around the Earth's orbit. If the asteroid's orbit goes inside of that torus, doesn't matter where the Earth is, but if the orbits are that close, then we say that's a potentially hazardous asteroid. We also expect them to be sort of 140 meters in size or larger before we consider them in this category. And just to keep the cartoon going here, here's a case of a potentially hazardous asteroid that's entering that torus right here, and so that's how it gets that label. A few words on where these asteroids come from and how they get into the near-Earth, into the inner solar system. Here you can see the main asteroid belt. That's the big yellow band around Mars. And what happens out there is that there's this network of resonances with Jupiter and Saturn. And radiation forces slowly push, especially the smaller main belt asteroids, into these resonances. Say the 3-to-1 orbital frequency resonance with Jupiter, so that there's 3 revolutions of the main belt asteroid every time that Jupiter has a single revolution. That resonance tends to pump up the eccentricity of the orbit, collapse the perihelion distance so that now it's entering the inner solar system. Then it can have interactions with the terrestrial planets and become decoupled from that Jupiter resonance. So that's how we get near-Earth asteroids to be fed into the inner solar system from the main belt. That's a constant feeding mechanism, and we have a sort of a steady state population because those near-Earth asteroids only have lifetimes of a few tens of millions of years because they're likely to wind up in the sun or on the surface of one of the terrestrial planets or have a strong interaction with Jupiter and get kicked back out of the inner solar system. What exactly do they look like? This is a picture of all the asteroids and comets that have been visited by spacecraft, and this is to scale, except there's 2 that aren't here, which would be sort of as big as the room or larger at this scale. Ceres is 900 kilometers, Vesta is 500 kilometers. Those aren't shown here. This bottom row here is the comets. This is Eros, the second largest near-Earth asteroid, about 33 kilometers long. It's not a problem for impact, thank goodness. Most of the NEAs are in this little U-shaped section over here. I call your attention in particular to Dimorphos. I don't know if you can see it, sort of 1 pixel over there. That's our prototypical 140-meter asteroid. Okay, and it's a satellite of Didymos, the one right above it. I've got a more detailed picture coming from the DART spacecraft, which I think we'll hear more about in the next talk. This is Didymos and its satellite Dimorphos. We know now that about 1 in 6 near-Earth asteroids are binary systems. We even have a few triple systems in the NEA population. DART got much closer to this thing, and that's what it looks like. This is the enemy, right? And it's not a big rock. This is a flying gravel pit cruising through the solar system looking for something to run into, and it has itself probably been run into many times. This collisional grinding process is the reason these things, we call them rubble piles, because at this size, we don't expect there are very many monolithic bodies in the population. How many are there? And where and how often do they hit? So this is, okay, I don't like this plot so much, but it's a physicist's conference, right? So I've got to show a log plot, I think. So you have diameter down here and the number of bodies on this axis, or the impact, the mean impact interval on that axis. So we could just go back to our 140-meter guy, and that's going to be these red squares here. You come over here, you've got about 25,000 of them, and their impact period is around 20,000 years is the mean interval. Just to maybe make it more accessible, we can look at a few of these random sizes. 4 meters, this is the size that hits the Earth about every year. No big deal. Flash, sonic boom, if you're lucky you can go there and collect meteorites. There's hundreds of millions of them, and we have discovered essentially none of them in a fractional sense. For the 25 meters, this is the Chelyabinsk scale. Now you start to have the possibility of some significant damage on the ground from an airburst explosion. And if it's over a populated area, remember Chelyabinsk missed the populated area, right? If it's over a populated area, it could be catastrophic for that urban area. There's millions of them, and again, we haven't really found any of them in a fractional sense. 140 meters, so the impact interval is about 20,000 years, and now bad things start to happen on the ground. If it hits the ground intact, it's going to make a large crater, devastate, say, the size, an area, a region, the size of a U.S. state or European country, as I mentioned. 25,000 we think exist, and we found about 40%. Now things start to get a little bit better. The damage is worse, but we found 95% of the 1-kilometer asteroids. So we're missing 1 in 20, actually less than that. And so this impact interval of 1 per 500,000 years, for the undiscovered population, you're really talking about 1 per 10 million years is the mean impact for the undiscovered population. And okay, the dinosaur killers, 10 kilometers, there's only a handful of them. We know where they all are. These are not the ones we're worried about. Okay, so what's to be done about this? Well, in the next talk, we're going to see that there are some things to be done if you know about the problem. So there's a variety of techniques for deflection have been proposed, studied, now even demonstrated, as we'll hear. If it's a small object with late warning, there may not be time to actually launch a space mission and eliminate the possibility of impact, but there's things you can do on the ground through civil defense, evacuation, sheltering, and so on, if you have time, and time is the key. So warning is the important thing. On this side of the slide, there's two perspectives. One is this cataloging and long-term warning, where we have, we're trying to get everything discovered, and we know where everything is and where it's going, and we know which ones we have to study more carefully. Some of the objects, especially the small ones, won't be found until late, and so you have this late warning of imminent impact. And so here we're talking about days or weeks, and that can be sort of all the difference between being surprised and being prepared. What's the technique for finding these things? I don't know if you can see in that astronomical image, there's this little guy moving right across the stars. This is how they find asteroids. They take multiple fields, images of the same star field, and any of the stars that move are not stars, they're asteroids. And so they put thousands and thousands of images into these moving object pipeline systems, and out comes positions of moving objects, which gets pumped over to the Minor Planet Center at the Center for Astrophysics in Cambridge, Massachusetts, and then it comes to us and we do our impact analysis. That information also goes out to the tracking and follow-up community, where they are constantly trying to improve the orbits of these things, especially shortly after they've been discovered. If we get lucky, it'll be big enough and close enough that we can get on it with radar telescopes like the Goldstone antenna, the 70-meter antenna in California. And there you get this exquisite precision in the measurements. You can get positions of the asteroid down to 5 or 10 meters in the position measurement. So very precise, and that really locks down the orbit for quite a while. Okay, how are we doing with this search program? Well, you can see in 1998, Congress sort of sat up straight in their chairs and said, oh my goodness, what's being done about this? Somebody should do something. And they said, NASA, go take care of this problem. And NASA has, I think, done a pretty good job. You can see in 98, things really started kicking off. And now here's this 140 meter, that's the orange or yellow curve there. We're making steady progress. More than one a day are being found on average. And our total catalog is upwards of 30,000. And as I mentioned, these kilometer-sized guys were almost saturated. That red curve is pretty much flat because we're not finding that many anymore, just a few per year. Who's doing the finding? Well, as I mentioned, NASA is really doing the heavy lifting here. They've got a space asset called NEOWISE, which some of you may know is a WISE spacecraft, was a astrophysics infrared survey. That was reactivated and repurposed as an asteroid search program. There's also this ATLAS program, which has 4 telescopes now in Hawaii, Chile, and South Africa. The Catalina Sky Survey has a couple of telescopes in Arizona, and Pan-STARRS has a couple of even larger telescopes on Maui in Hawaii. And I should mention there's this linear SST, which is a US military program that does share data with us. They are also not prone to oversharing, and so there's some latency in the delivery of data. So they're not discovering anything to speak of because of the delays, but they are providing a lot of data that helps us refine the orbits after they've been discovered. And who's finding what? I mentioned Pan-STARRS is the pink, and Catalina is the green. They are doing most of the discoveries. These are for the 140 meters. You can see for the last 10 or 20 years, we've been finding this same steady 400 or so objects per year. And then these the 2 green ones, that's NEOWISE and ATLAS, some other American surveys. And then the gray is the rest of the world's contribution. Which isn't to say they aren't doing anything, but this isn't where they've decided to make their mark on the problem. I should be clear about that. Although in that gray, there's a productive system in China, also some smaller programs in Europe that are working on this. But as you can see, this is substantially being done by American efforts. LSST, speaking about next generation surveys, is really going to boost things. And LSST is no longer vaporware, right? This is a photograph, not an artist's rendition of the telescope, the Vera Rubin Observatory in Chile. And here you can see the lower red line is what would happen without LSST, and the upper red line is where LSST is going to drive the discoveries to. And this is, again, for those 140-meter class asteroids. We also have an upcoming space-based half-meter infrared survey. This is it's going to fly in 4, maybe 5 years from now. It's dedicated to near-Earth asteroid search and characterization. So this isn't something that NASA has never done, is to put a dedicated space observatory up for this problem. And it's going to, between LSST and Surveyor, our 40% completion on those 140 meters is going to go quickly up to about 90% in about 10 years. Okay, let me see how I'm doing on time. So I want to tell one little short story about how finding these things can be a little tricky. This is something that was discovered last summer and came actually fairly close to the Earth, about 13 lunar distances. And this kind of crazy plot is a rotating frame. So the Earth is at the center, the sun is at the center, and the Earth is always here to the right of the sun. As the Earth revolves, we rotate the reference frame to keep the Earth at the same position in this depiction. That makes the asteroid do this kind of crazy spirograph approach in the rotating frame, but it's very convenient, so we can see that until it actually came so close to the Earth in 2022, the previous 2 decades, it never came into this search zone, which is the gold region here. It never came into the zone where it could have been discovered by the Earth. And eventually it did, of course, and there it is, we found it. But if we'd had NEO Surveyor and looking at where it could be searching, you can see that it would have come into the NEO Surveyor's space-based search region many times in those 2 decades. And this is the reason NEO Surveyor is going to help clean up the catalog quite a lot. Okay, a little plug for our Center for Near Earth Object Studies at JPL. We are the NASA's Center for Computing Asteroid and Comet Orbits, and importantly, computing the odds of Earth impact. And this is our webpage, and this is our kind of our charter, you could say. And one of the things we do there is this impact monitoring. When I got into this business 24 or 5 years ago, there was a lot of early detection going on and no early warning. There were objects that had potential impacts that were going lost because nobody knew about them. And so that was the point at which we said, we've got to actually stand up these fully automated robotic systems that are continually mining the catalog and looking for possibilities of impact so they can be followed up, tracked, and those possibilities of impact eliminated. So the analogy I like to use is this hurricane tracking. So you can have, say, early on, this cone is threatening Oahu, but later you get more data, time passes, and it can go to the west or to the east, or possibly it could stay on Oahu, and as time passes further, suddenly you realize it's not only Oahu, but it's Honolulu that's at risk, okay? So this is the scheme for asteroids. It's really the same. We reduce it to a 2-dimensional problem. This is what we call a target plane. Okay, it's a schematic, but this is our target plane. And this is the view, essentially, that the asteroid sees out the front window as it's approaching the Earth. And it's going to fly by the Earth at some distance. And there's the Earth in green. And initially, there will be some large footprint with a position prediction and uncertainty. And then as time passes, and at that stage, we have a computable impact probability. As time passes, we get a smaller footprint with more data, and the Earth is still in there, the impact probability goes up. And then finally, it goes off, and then we can say, okay, it's not, an impact is no longer possible. So you can reduce this to kind of a toy problem, but a toy problem that works really well. If we want to know what the evolution of the impact probability will be, we need to know the encounter uncertainty. That's the size of that ellipse I showed you. And this is measured in terms of Earth radii in this depiction. And here's the impact probability that we're going to compute. And as we first start the problem, we're down on this, we're moving up this ramp because this encounter uncertainty is going down. We're moving to the right. Essentially, you can think about that x-axis as time, but it's not smooth because we get data in chunks. And so we can go, lumpty, lumpty, lumpty along that x-axis. However close this asteroid is going to pass determines how high it's going to rise. So it goes up the ramp, and if it's going to go to 10 Earth radii, that's the true miss distance, then it's going to go all the way up to here. It's going to reach a few percent impact probability and then collapse. That's the drill. It's intrinsic to the way we do this. And it's a problem sometimes because it gets worse, then it gets better, and we expect it, but not everybody expects it. So early on, we have this problem where in the newspapers, they were reporting on embarrassing retractions from astronomers or false alarms because, hey, they said it was going to hit, even though we just said there was a chance it was going to hit. But then we had said later, no, not going to hit anymore. Well, that sounds like a false alarm. Sounds like a retraction. We were told we needed to start checking our figures better before we notify the observing community about these things. We have this idea of crying wolf. You do this too many times, nobody's going to listen to you anymore. I think the opposite has taken place. This Mithridatism idea that small doses of poison will leave you well prepared to survive a large dose of poison. You get used to it. And when something really serious comes along, you're going to go into it with eyes wide open and have a reasonable reaction. And I think that's the situation we find ourselves in. Key to that success is the openness that we have. Secrecy in this arena is corrosive. It's too rich for conspiracy theories and so on, that any kind of secrecy would be disastrous. And so we are always completely open. And as an example, I mentioned there's these two kinds of impact monitoring, the long term and the short term. The long term we call a sentry. It's a completely different tool from the short term that I'll talk about next. This is the deep search. I have this straight-laced, well-organized sentry here. This is the analog, because first they have to get discovered, then they have to get confirmed, then they have to get formally announced as a new discovery. This process can take 3 to 5 days. And then Sentry gets turned on, and it does its deep, deep search, leaving no stone unturned, looking out for 100 years to find any possibilities of impact. In contrast, there's the Scout system, and it is sort of in the weeds. It's working with data that's not been confirmed. It's dirty. A lot of this stuff is not even real. These are telescope artifacts, camera artifacts, spacecraft. There's a lot of junk that goes through this process, but there's also a lot of real stuff, as I'll show you. And so the idea is that we want to find out as early as possible, and then this is a public web page, just like Sentry, and we have this, where can I find it? Impact rating, okay? The impact rating tells people whether this is particularly interesting, and they should get their telescopes on it right away. That's worked out well. I mentioned on the title slide, this 2022 WJ1, it was discovered 3 hours before impact. With 4 observations over less than a half hour, we had a 25% probability of impact. That alert went out from Scout 20 minutes after discovery, and that led to more observations. So we got 8 observations at 50% probability of impact, and you can see the footprint on the ground. And finally, with only 12 observations over a little more than an hour, we were at 100% probability of impact. We got more data, and that footprint on the ground continued to shrink and shrink and shrink until it was just a kilometer or so. And here's the picture Rob Warwick took. Crazy thing, he lives in Ontario. He works for the Hawaii Survey, Pan-STARRS, but it went right over his neighborhood. So somebody got him out of bed, and he went with his tripod and took this fantastic picture. There's a world-class all-sky camera network for tracking fireballs at the University of Western Ontario. It went right over their network. And there's this gorgeous picture of the thing flying behind the CN Tower in Toronto. And here is just a Google Earth representation of the final descent down to the surface. It missed the lakes, and so in principle you can get meteorites, but this was right after one of those polar vortexes came through. Like, I think it's happening outside right now. And so there was not a good opportunity for finding meteorites, although it's possible once the snow melts, if it ever does in Ontario, that they'll find some meteorites. Okay, so wrapping up, Sentry and Scout are our 2 impact monitoring systems and at the Center for Near-Earth Object Studies at JPL. There's the Scout short-term hazard with poorly constrained orbits. Here, the nonlinearity that we're wrestling with is in the orbit determination problem. And then Sentry, for longer-term hazard out 100 years, there, the orbit determination is actually linear, but that propagation for 100 years through multiple planetary encounters is highly nonlinear. So the techniques used are very different. All our results are publicly available immediately, and we think that's a good thing, although not everybody shares that opinion. Some of you may know about the episode of The Simpsons where Bart discovers a comet inbound to Springfield. Chaos ensues, panic, pushing, shoving. They tried to deflect it with a missile that destroys the only bridge out of town. It's a disaster. So ever the wise, Mo the bartender said, let's go burn down the observatory so this will never happen again. Okay, that's the other way of solving the problem. That's where I'll stop.
Steve finished a little ahead of time, so there's plenty of time for questions. Since the entire proceeding is being recorded, please, if you'd like to ask a question, go to the microphone. While people are doing that, let me start by asking a question. You talked about all the US efforts. What about the rest of the world?
Well, they're doing things. I wouldn't, for example, we'll hear about the DART mission, which actually did a demonstration of a deflection at the Dimorphos asteroid. The Europeans are sending a mission now to better understand that system, and that should be launching, I think, within a year or so. There's data centers in Europe that are doing the same kind of monitoring that we do at JPL. And so in the good sense, this is a redundancy where we have this robustness and mutual verification. So the Europeans are also doing this impact monitoring that we do at JPL.
I was just curious, when you were showing the percentage of different sized ones that you've discovered, how you know how many there should be? Like, where does that model come from, and how confident are you that you've discovered 95% or 100% of a given size?
Yeah, that's a great question, and there's, as you might imagine, there's a vast literature on this problem. One way to think about it, the simplest way of thinking about it is if you're looking at you're running your telescope and 90% of what you detect is already in the catalog. Then, with a whole bunch of little fine-tuning details, you could say that you've discovered 90% of the population at that size. So the idea that we know how much we're detecting and how fast we're detecting new stuff tells us how much stuff remains to be detected. That's a great question. And there's other techniques too that are more technical, but.
Yeah, thank you for the talk. I was wondering how much does the radius of impact shrink as a function of time before impact? So, like you said that when it hit New York, that it was like 1 kilometer radius or something. But how quickly can you know that, and can you notify people in enough time to get them to actually leave the area if they need to?
So for our good luck, we've never had one big enough that we had to think about that question. But the way it works is that it takes time and it takes data to get that forecast to be small. But in the case, we knew that was going to be hitting at 50 kilometers altitude right over Brantford, Ontario. And we knew that within 10 kilometers pretty early. We also knew this was a meter-ish size object, and we didn't need to go call the Brantfield authorities. For our good luck, the bigger ones come less often, and they get discovered earlier because they're brighter. And so if we have something like Chelyabinsk coming from the nighttime sky, we're going to have about 2 weeks of time when it would be discovered. Chelyabinsk came out of the daytime sky. It was a complete surprise. Half of them are going to come out of the nighttime sky, and if they're that big, they would be discovered a couple of weeks in advance. And we would, within a few days, have it down to a small enough area that you can start to actually develop evacuation plans or other kinds of civil defense measures.
So the one in Russia was unlucky that you didn't see it before.
We're never going to get, well, maybe 20 meters, maybe we could eventually catalog all of those guys, but half of them are always going to come out of the daytime sky. And if they're small, cataloging when there's millions and millions of objects at that size, it's just not feasible. And so there's a coin toss involved.
Yeah, so there's also space junk, and that's a different community that's monitoring that. But I'm just wondering if you can make some comment about overlap in data between what you might see, or is it a completely different technology to look for it?
No, it's not completely different. The time scales are different, right? So one is the space junk is on a sort of a 90-minute orbit, and the asteroids are coming by at say 10 or 20 kilometers per second, and they only come by once. And so the time scales are different, but the data types are really the same in that I showed you that SST telescope run by the military. That is for space surveillance and space debris tracking. They want to know where all their stuff is. They also want to know where the other guy's stuff is. And they're also responsible for tracking all the inert stuff in space. We interact with the Space Command in our office, because whenever an asteroid comes close enough to be a potential hazard to orbiting assets, we coordinate with them so that we can make sure that it's deconflicted with anything on orbit. But the data types and the survey approaches are really the same.
After they're built and they come online, do you plan on incorporating the ELT telescopes, like the 30-meter telescopes, in your Sentry program?
I don't know much about these large, extremely large, or TMT probably is another one I know about. I'm kind of doubtful that those are going to be suitable for search or follow-up. Our follow-up instruments, perfectly adequate to have 2 or 4 meter in the most interesting cases. Most of our follow-up facilities are 1 to 2 meters in aperture. And we also need to do search, we need to have the telescope all the time. And nobody's going to give us TMT all the time. But LSST, I will mention, is I think an 8 meter, 6 meter effective aperture. And that is surveying for asteroids all the time, even while it's also doing supernovas and GRBs and everything else that it's doing. We're getting a lot of data all the time from LSST. Yes.
Thanks for a great talk. When calculating the impact locations, is the major contributor to the uncertainty more the measurements that you take, or is it computational power or something else?
The major contributor to
The uncertainty in where the impact is going to be.
So the uncertainty in our measurements maps directly into the uncertainty in our prediction. And we have spent over the last many years a lot of time trying to make sure that we are properly characterizing the uncertainties, because a lot of the data comes to us with no uncertainty information. We know that there's star catalog biases at play. We know that there's a number of error sources that are variable from time to time, telescope to telescope, night to night. And so we spent a lot of time making sure that we have the right statistical treatment on our data, because that maps directly to the prediction uncertainty. And I say we do pretty well, and we're always checking. When we find a prediction that turns out to be poor, we go back to the data and we find out what went wrong, and we sometimes will tweak our models. But there's always outliers, and it's hard sometimes to recognize outliers, especially in sparse data sets. And so we have been burned in the past.
Time for
by
one
outliers.
last brief question and brief response.
All right. Hey, thanks again for a great talk. I noticed in that Sentry database that was on the screen, it was saying like in the next 100 years. I was wondering, is that like a computational thing that there's just like so much data that it's not feasible to do these calculations for things that are likely to collide beyond that time? Or is that being done? Like, is it possible there's something that is like, we know it has actually a reasonably high chance, but it's like 200 years away? Or is that just like not a thing we know?
Well, I'll be retired after that. But that's only half the story. I mean, there is 100 years is kind of a round number. There are on that table a small handful of objects with farther out impact probabilities that we've sort of stumbled on and not found in a systematic way. There's one 1950 DA where its impact is about 900 years in the future from now. This is one of those kilometer-sized objects, and so it's been a subject of a lot of study. But that's there, 1950 DA, 900 years out. But the systematic, exhaustive searches are out for 100 years, which is long enough for me to be out of the way.
Let's thank Steve Chesley.
Sounds like everybody can hear me okay. All right, so today I'm going to be talking to you about planetary defense in the age of DART. Following on from all the information that Steve has just shared with you. Here on the title slide, you can see an image of one of the asteroids that Steve spoke of, Dimorphos, the secondary body of the Didymos binary asteroid system. Dimorphos is, roughly speaking, about 160 meters across, and as Steve pointed out, its structure is a rubble pile structure, a large aggregate of material that's primarily held together by mutual gravity. Steve's already showed this chart, so I won't spend too much time on it, but what I will point out is that somewhere between the 25 and the 140 meter asteroid size is the size of the asteroid that would be able to penetrate the atmosphere deeply enough to cause serious harm on the ground as opposed to detonating up at altitude. Asteroids larger than that will penetrate more easily. Asteroids smaller than that are more likely to break up at altitude. And then at the same time, you have to consider how easy it is for us to interact with those objects in space. So when you reduce those factors, it seems like roughly 50 meters is about the smallest object for which we would probably care to try to send a space mission. If it's smaller than that, we probably wouldn't have enough warning to do so anyhow, and civil defense measures on the ground might be the more appropriate response. So Dimorphos, as Steve pointed out, is an example of this approximately 140 meter size object, which NASA is congressionally tasked to discover the majority of because of their ability to do such grave harm on the ground. And certainly asteroids larger than that, the damage gets worse. Steve also showed this chart, which is just to say that we get hit by small objects very frequently. Steve showed that the population roughly follows a power law. It's not exactly a power law, but it's pretty close. And that means that the small objects are just vastly more numerous than the larger objects. And so we're going to get hit by the small ones a lot more frequently. But occasionally something large enough to get our attention, like Chelyabinsk, comes in. And so for that reason, we need to be prepared. This chart here shows NASA's approach to this, to the planetary defense problem. We search, detect, and track using the telescopes that Steve described. We also use those telescopes and radar facilities to characterize the objects. We plan and coordinate both at the interagency level within the US government and also at the international level to deal with these objects, to aggregate these data sets, to plan missions when necessary. And then we prepare ourselves to perform mitigation missions. So that is to go up and deflect or destroy asteroids or comets before they can strike, assuming we have enough advance notice and enough infrastructure in place and tested, which is very much what the DART mission was all about. And then we assess the population. So Steve talked about the Center for Near-Earth Object Studies, or CNEOS, a website that you can go to where all the data is made publicly available from Scout, Sentry, other systems as well, NATS, which looks for mission opportunities to visit these objects. All of those data are made available online. And so DART, which is what I'm going to be concentrating on today, is the first mitigation demonstration mission that humanity has ever undertaken to an asteroid. And all of this is being run by NASA's Planetary Defense Coordination Office, or PDCO, which was first established in early 2016. Now, this is all part of a larger plan. Here, I'm talking about the National Near-Earth Object Preparedness Strategy and Action Plan, which was a White House document written and published in June of 2018. There's a new version of it that was just recently published a couple weeks ago, so I encourage you to go online and look it up. It's an updated version of the original plan to account for the things that we've accomplished since 2018 in the way that our knowledge and our thinking have evolved in terms of what we want to do next. DART is important to goal 3 in the plan. There are 5 goals laid out in the original plan, and goal 3 is all about becoming prepared to deflect or disrupt an NEO. Now, Steve pointed out in his talk that, well, you see, we think we've discovered the vast majority of the large objects, and there's a very large population of undiscovered medium to small size objects that could still cause grave harm, and that's why we're concentrating on that, because they're very numerous and we have a pretty good idea that they're out there. But what also is important to mention is that there are comets too, which sort of fall outside of that. So there's the near-Earth asteroid population, and those are on reasonably well-bound orbits in the inner solar system, and we can track them and so on and so forth. And then there are long period or single apparition comets that come diving in from the distant reaches of the solar system and make one perihelion pass, and then off they go. An example of this was comet Siding Spring, which in October of 2014 almost hit Mars. It came really, really close. And we discovered that comet roughly about a year and a half, I think, before it almost hit Mars. And that's sort of a prototypical example of the sort of thing that can happen. And it's fortunately very rare. We think that comet approaches like that are even more rare than the strikes by some of the larger size asteroids. And so, we have that in our favor. But, these are aperiodic events. We can calculate average intervals in a statistical sense between events of certain energy levels, impact events of certain energy levels, but that doesn't give us any predictive power about when the next one's going to happen. And so that's why vigilance and preparedness is so important. So that drives us to study how we might deal with these objects. And so I'm going to talk now a bit about mitigation techniques. So this chart right here was published in 2010 by the National Academies in the Defending Planet Earth report. And what this does is it cross-references warning time in years on the horizontal axis with diameter in meters on the vertical axis. And so what this plot shows is that there are 3 techniques that at the time were considered to be the most technologically mature. Nuclear explosive devices, kinetic impactors, of which DART is an example, and gravity tractors. So the gravity tractor is a spacecraft that rendezvous with the asteroid, parks next to it, station keeps propulsively to maintain distance, fighting the asteroid's very weak gravity that would pull the spacecraft towards the asteroid. The spacecraft's thrusters counteract that, and so then the gravity of the spacecraft itself tugs on the asteroid, and over a long period of time changes the asteroid's orbit around the sun. And so because that's a very small effect, because the mass of a spacecraft is naturally limited, that's really only well suited to very long warning times, so the several decade level. Kinetic impactors is sort of the next most effective thing, and that might be effective on roughly the decade level, but you're better off if you've got more time than that. And it's also limited in the size of object that it can handle even at longer warning times. And that's just because of the physics of momentum exchange between a spacecraft and an asteroid, which I'm going to elaborate on later in the DART context. In the kinetic impactor, it's just ramming a spacecraft right into the asteroid at high velocity. So think greater than 5 kilometers per second, roughly speaking. The gravity tractor requires that you rendezvous. You got to stop at the asteroid. You can't come screaming in. You got to stop and park in order for it to do its job. Rendezvous opportunities for spacecraft are more limited than high-speed intercept opportunities, all else being equal. So that's a limitation for the gravity tractor. The kinetic impactor has to come screaming in order to do its job, or it won't work. Well, you have more mission opportunities, more launch opportunities, but then you have a really tough terminal guidance problem. You're coming screaming in at 10 to 20,000 miles per hour against this thing that you can't even really see in your camera until you're almost on top of it. It's a very, very hard problem. DART put the first big dent in showing that we can solve that problem in at least some regimes. And then you've got the standoff nuclear detonation. So in that case, you position the nuclear device close to the asteroid, you detonate it. When I say close, I'm talking tens to maybe a couple hundreds of meters from the surface of the asteroid. There's an optimal height of burst that's associated with the asteroid, depending on the asteroid size and the yield of the device. And so then the radiation released by the nuclear explosive will irradiate the surface area of the asteroid that sees the radiation as a function of the geometry. So think of like a little spherical cap of a spherical asteroid is getting irradiated down to depths of maybe a few centimeters, roughly speaking. It depends on the spectrum of the device, but which is mostly going to be X-rays. And so it superheats the material, it vaporizes it, and it ablates and blows off to zero pressure. And that rapid blow-off of material induces a delta velocity in the asteroid in the opposite direction, gives it a nice hard push. And so because the energy density of nuclear devices is so much higher than that of a kinetic impactor, for a relatively small amount of nuclear device mass, you can obtain a very large delta velocity on an asteroid. And the reason why we care about changing the speed of the asteroid is because that's how we put the asteroid onto a slightly different orbit around the sun from its natural orbit that will then go on to miss the Earth later. I should also point out that the kinetic impactor, even though it's several orders of magnitude less energy density than a nuclear device, has a higher energy density than our best chemical explosives. So you're not going to gain anything by putting chemical explosives on a kinetic impactor. There are other ways to couple a nuclear device to an asteroid besides a standoff burst. You can do things like try to get it below the surface of the asteroid and other things that might enhance the coupling of the energy between the nuke and the asteroid. But those are really hard to do logistically. Detonating off at a distance from the asteroid is much easier, and modeling shows that it's very effective. So that's usually what we concentrate on. Now, the nuclear device, it's best if you rendezvous, stop and park at the asteroid, because then you can have exquisite control over where you position the device, and you can be very well informed about where you position the device. But it also is possible to detonate in a high-speed proximity fusing system as you're approaching the asteroid at hypervelocity, just like a kinetic impactor. So the nuclear device can walk in both worlds, high-speed intercept or rendezvous. DART is an example of the kinetic impactor at roughly the 150, 160 meter sized target level. Now that chart that I just showed you has been updated in recent years to include another technique called IBD, ion beam deflection, where you take the plume of an ion thruster and point it at the asteroid deliberately to let the momentum of the ions impinge on the asteroid and transfer momentum to the asteroid that way. And when you do the math and you reduce things to a kilogram versus kilogram level, kinetic impactors and ion beam deflection systems perform comparably, and so they sort of get lumped together here on this chart. I haven't talked much about disruption yet, but if you impart a high enough delta velocity to the asteroid, you're going to set up a shock wave inside of it that's going to blow it apart fundamentally, which is not all that hard to do because we don't think that the asteroids have a lot of intrinsic strength to speak of. And so the nuclear devices can certainly impart a large enough delta velocity to accomplish a complete disruption. We aim for what we call robust disruption, which means that we break the object up into a lot of really small pieces that are all widely enough scattered that the vast majority, 99.99% of the asteroid's original mass will go on to miss the Earth, and any remaining fragments, the largest of them would be small enough to be dealt with by the atmosphere. So that's what we define as robust disruption. And current modeling research is aimed at figuring out how we can best ensure in a given scenario that we could indeed accomplish that, to have some certainty that we would get the result that we wanted there. Now, it is possible to impart enough specific energy, that is energy per unit mass of asteroid with a kinetic impactor to theoretically disrupt the asteroid, but only for smaller asteroid sizes than what you could disrupt in a nuclear engagement. So that brings us to the DART mission. In the interest of becoming prepared, we have to test any system that we're ever going to rely upon during a true emergency to be sure that it works the way that we think it will, and to solve the technical problems in its implementation that might prevent it from working when it's needed. So DART had four main level 1 requirements. The first was just to hit the target. I told you it's really hard. And I'll show you some movies, some flight data, that illustrate this. It's really hard to hit a small target when you're going fast. So the first requirement was just to hit. Secondly, to change the binary asteroid period by at least 73 seconds, because we believe that would be measurable. And even in the case of a grazing impact, we believe we could get at least a 73-second period change. Measure that period change to a 1 sigma accuracy of plus or minus 7.3 seconds, also because that's achievable using ground-based observatories. And then measure the so-called beta factor, that is the momentum enhancement factor, and characterize the impact dynamics. So you can see here a hydrocode simulation of a hypervelocity impact. And so remember that momentum and energy are conserved separately. So what that means is that in addition to the momentum that's brought in by the spacecraft, the energy of the impact is going to excavate a crater and mobilize material out of the crater. And that material that comes out of the crater has mass and velocity and therefore carries momentum of its own, which then goes into the momentum balance. And so that means that the ejecta that comes out of the impact crater can cause the asteroid's velocity to be changed by more than what the spacecraft's impact could have accomplished alone. But just exactly how much extra velocity change you're going to get on the asteroid is a complete unknown. We have a lot of simulations like this one and a lot of models that say that it could be anywhere from virtually no enhancement to maybe a factor of 5 or 6 of, beyond what you would have gotten without the ejecta. Well, that's a really broad range. And so for people who plan missions, which is what I do, I need to know what that beta factor is or is likely to be so I can build that into my planning, because I need to know, well, how many kinetic impactors do I really need to deflect asteroid so-and-so? Well, it depends on what beta is. So we've got all these models, we got this big range for what beta could be. It was time to do a real field experiment and get our first data point and find out exactly how it behaves, at least in this particular case. Okay, so here is Didymos, the parent body of the Didymos binary asteroid system, about 780 meters across. There's Dimorphos, about 163 meters across, comparable to the Great Pyramid. And DART is like the size of a bus. It's about 19 meters wingtip to wingtip. Didymos is like the size of a small mountain or a large building there. So gives you a sense of scale. Here's what DART looks like. It's got these long solar arrays, sort of a cube-shaped bus in the middle. Draco is the only and primary instrument on the spacecraft. It's a camera that's used to lock onto the asteroid and guide in. We also had LiCiCube. The Italian Space Agency built a 6U CubeSat that we deployed a little over a week from the asteroid intercept. And LiCiCube was able to sail on by at 6 kilometers per second and sort of pivot and take pictures as it went and give us sort of a in situ view that we wouldn't have had otherwise, because there was no other spacecraft to accompany DART. The original plan was for the European Space Agency to send a rendezvous mission to the asteroid before DART got there, so that rendezvous spacecraft could observe what happened. And in a real planetary defense scenario, that's precisely what we would endeavor to do. You want to have situational awareness and all the data that you get from having eyes on the target. Well, that just wasn't in the cards. They weren't able to send that mission. So DART had to fly alone. But as I'll show you, we designed DART to be doable even without the observer being there in advance. And we accomplished that by choosing a time to intercept Didymos when Didymos was naturally very close to the Earth, which means that our Earth-based observing assets and assets like the Hubble Space Telescope could get a good enough view to give us enough data to accomplish the measurements laid out in DART's requirements. And DART was also an opportunity to test some new technologies. These rollout solar arrays, the Next-C ion thruster, the SmartNav software that guided the spacecraft into impact, this radial line slot array, communications antenna. So DART was an opportunity to test out and demonstrate some new technologies at the same time as we did our very first planetary defense test. Okay, so here's a close-up of what LiCiCube looked like. It had 2 cameras called Luke and Leia. It got to within about 55 kilometers of Didymos. Or rather, I should say Dimorphos. This is DART being loaded in the nose cone of the Falcon 9 rocket that launched November 2021 out of Vandenberg Space Force Base. A spectacular launch, a night launch, a really, really awesome sight to witness. And then here's a schematic that sort of lays out the main events of the mission. So LiCiCube is deployed, DART comes in, it's a mass of about 580 kilograms at impact, coming in at 6.1 kilometers per second, or about 14,000 miles per hour, striking Didymos at 7:14 p.m. Eastern Time, September 26th of last year. At that time, the orbital separation distance between the bodies was about 1,200 meters, and Earth was about 7 million miles away at that point. So this animation here shows the mission trajectory. So you can see Earth coming around here. There's Didymos. You can see where the closest approach between Didymos and the Earth is. DART has launched, and DART launched into a sort of Earth-like orbit. I mean, you can see DART is not really getting all that far away from the Earth as they both fall in free fall around the sun together. And then Didymos is falling around the sun, and they're all going to come together right around here. And that was by design. We chose Didymos partially for this reason, and we chose the timing of the mission also for this reason. So here is another animation that shows how the binary asteroid system works. So the 2 objects are orbiting their common center of mass. Didymos is there in the center. Here's Dimorphos going around. Earth is observing this, and the Didymos system was discovered in 1996, and it's been extensively observed by telescopes, and it's been measured by planetary radar when it's been close enough to the Earth for that. So DART deployed LiCiCube. LiCiCube flew past while DART impacted. And the DART impact placed Dimorphos onto a new orbit, different from the original orbit. It slowed Dimorphos down, so it dropped the orbit radius a bit on the opposite side. And the original orbit period was on the order of about 11 hours and 55 minutes. And I remember I said we had to change it by at least 73 seconds. Well, we changed it by quite a bit more than that. We wound up changing it by about 33 minutes. So we made a very significant change in the orbit period of the asteroid. So post-impact orbital period, 11 hours and 22 minutes. All right, so I'm going to move a little bit more quickly through some of this just so we have enough time. About 4 hours before impact, the SmartNav system took over and the spacecraft went fully autonomous because there isn't enough time due to the light time delay and the speed at which things are happening to turn around ground command. So the spacecraft has to be able to do everything by itself. So we're about 90,000 kilometers out at that point. The last maneuver was performed about 2.5 minutes out, and the last complete image came at 2 seconds before impact at a distance of 12 kilometers. And you can see the system becoming more visible as we come in. So this is 4 hours before impact, 90,000 kilometers, 73 minutes before impact, 27,000 kilometers, 50 minutes before impact, 18,000 kilometers. You just start to see Dimorphos there. And then here is the actual image data collected during the final 5 minutes of the approach. And so you can see that the SmartNav system is identifying features. It's designed to be able to distinguish between Didymos and Dimorphos so that it doesn't accidentally lock onto the larger body, locks onto the intended target here. This is obviously sped up quite a bit, and then we'll reduce the speed of the playback here as we get closer and closer to impact. We were all watching this as it happened. It was broadcast live too. And then when we saw that partial frame come in, we knew that was it. We'd hit the asteroid, which is exactly what we wanted to see. So here is an image about 2.5 minutes before impact. This is a close-up of the surface. You can see it's really rocky, really rubbly. We knew as soon as we could see it starting to fill the field of view of the camera that we were looking at a rubble pile. You know, you can imagine all sorts of formation scenarios, or how do you get a binary asteroid? You know, Didymos is spinning at about 2.2-hour orbital period. And when you do the math, it turns out that that's almost critical rotation period, where a strengthless object would start to lose material off the equator because it was spinning so fast. 2.2 hours, it's a function of density, but that's about what it is. And so, you know, and so you can imagine these objects spin up, you know, from solar radiation and thermal effects, and then they fling material off the equator, and then the material reaggregates. And then there's other ideas that maybe there's a large impact that knocks a lot of material off, but it doesn't escape gravitationally, and so it reaggregates. And so, you know, you can imagine all this rubble sort of coming together and clumping up to form an object like Dimorphos orbiting around Didymos. So this is the impact point here, and this is our reconstruction of what the spacecraft orientation relative to the surface was at impact. And here's a 3D rendering showing how we think it sort of nestled the solar rays between some of the local topography. And this is the final high-resolution mosaic image made from the last 10 Draco images that came down. Here's an image from LICIACube. This is from the Luke camera about 3 minutes after impact. Obviously, a lot of sunlight being reflected off of all that debris kicked off. You can also see in this image here how wide the opening angle is of the ejecta cone. And so we made a lot of ejecta. We changed the asteroid's period by a lot more than the minimum requirement. We had this really big wide opening cone. We saw in the images that object looks really rubble pile-y. And so this is all consistent with simulation results. You expect a big wide ejecta cone. You expect a lot of ejecta from an object that doesn't have a lot of intrinsic strength. So here's the animation showing the LICIACube images as they were collected. And so LICIACube is zooming on by, and now it's past and moving away. And then this is a composite image where we've stacked together some images with different levels of contrast so that we can sort of see some of the differences in the fine structure of the ejecta. And it's a fairly striking image. So all of these data were collected by a whole network of ground telescopes, as well as Hubble, JWST, and even the Lucy spacecraft took some images. Here's a smattering of images from all around the world. This is Hubble, 5 hours post-impact, and JWST, 5 hours post-impact. Hubble, 12 days after impact, you can see this bifurcated tail, which is very interesting. And here from the Very Large Telescope in Chile, you can sort of see this pinwheel effect where you've got material coming off in different directions. This is 0 through 29 days post-impact. So you've got the binary asteroid system having its mutual orbit, and you've got the bodies rotating. And so you can imagine that material gets flung off in different directions before eventually the sun pushes everything away from the sun and you develop a tail, which is exactly what happened. So we gave an asteroid a tail and made our own little comet, but it's not really a comet. And if you stack images for like an hour and using Hubble, you can still barely see the tail, even today. And so here's an example of how we measure the orbit period change. Fundamentally, we look at when the object passes in front of the or when Dimorphos passes in front of Didymos and passes behind it. And we measure the changes in brightness, and from that we can get the orbit, the mutual orbit period. And I will move through this real quickly. We also use the Goldstone planetary radar that Steve spoke of. Here is Didymos. There is Dimorphos down here. And indeed, Dimorphos is offset from where we thought it would be by exactly the same amount that the telescopic orbit period measurement said it would be offset. So the retail stretches a distance behind the asteroid that goes almost all the way around the Earth in terms of length scale comparison. And a lot of ejecta came off, somewhere between 6 to 60 rail cars worth of ejecta. Well over several million kilograms worth of ejecta came out. Here is just a depiction of what the momentum enhancement factor means. If you get some ejecta, you get a moderate or a modest enhancement factor. Lots of ejecta, you get a big momentum enhancement factor. For DART, we calculated a factor of about 3.6, and I'll show you how we did that in a minute. This is the basic equation that you use. This is the momentum balance, which includes the change in velocity on the asteroid. The asteroid's mass is here. Spacecraft mass is here. Velocity relative to the asteroid is here. And then this term here expresses the momentum carried by the ejecta along the direction of the mean momentum direction of the ejecta, let's say. Scaled in terms of spacecraft mass. That's what beta does for you. So a beta of 1 means that there was no ejecta. A beta of 2 means you got as much momentum from the ejecta as the spacecraft brought in, and then beta greater than 2 means the ejecta carried more momentum than what the spacecraft brought in. And you can see the relative geometry of the impact here. E sub t is the direction of Dimorphos' velocity around Didymos. And so the approach direction of the spacecraft, what we think the mean ejecta direction is, and the orbital direction are all, in kind of a small cone there. There's not a large disparity in directions. And what we did is, because we can't measure the full delta V vector because we didn't have an observer spacecraft there, we did a little transformation here. We took the dot product with the direction of the Dimorphos' orbital velocity through this equation. And so what that does is it allows us to express everything in terms of the so-called along track or velocity direction component of the delta V that's in the direction of Dimorphos' velocity. That we can measure because that plays directly into the orbital period, and the change in orbital period is measurable. So that's how we tie all this together. And then we can solve for beta. And this is all in the Nature paper that we just recently published. So we did a Monte Carlo analysis to account for all the uncertainties in the system, the uncertainties in the original orbit radius, the uncertainty in the period change, the uncertainty in the size and the density and all the systematics. And so we found a mean result of negative 2.7 millimeters per second for the along track velocity change. And then when we combine that and run that through the beta equation, and we do an additional Monte Carlo on what the actual ejecta cone direction was, we get the full Monte Carlo result for beta, which has a mean value of about 3.6, if you assume that Dimorphos' density is the same as the system density, because we can measure the mass of the total system as it orbits its common center of mass, but we can't measure the mass of either asteroid individually. So we don't know how the mass is apportioned between the bodies, and that's the largest unknown in calculating beta. So, Dimorphos' mass, could range, between a fairly large array of values. But anyway, if you cut down the middle there, you find a value of about 3.6 for beta. So that means that going forward for planning planetary defense missions, instead of the conservative assumption for kinetic impact or design being, well, let's just assume that we get nothing from the ejecta and beta is 1, well, you're probably better off assuming at least a beta of 2, maybe a beta of 3. We feel comfortable saying, we should probably look to see beta values that are approaching this range conservatively. But of course, it's a data point of 1, and more missions and more testing are something that we look forward to doing. Steve mentioned the Hera mission is going to rendezvous with the asteroid in 2026, and we're going to get a lot more data about it then that we can combine with the data we've collected now and learn even more. And I encourage you to check out the DART website. We have a lot of resources and additional information there if you're interested. That's it.
So we only have time for 1 or 2 brief questions. Right, go ahead.
Okay, my question is, how well did the modeling come out before the DART mission? I had a lot of conversations with Doug Hamilton, Derek Richardson at Maryland and others, and there was a lot of uncertainty. How well did their modeling do? One thing I noticed was, at least maybe it was just the cartoon, the rocket effect was very narrow on the diagram, but the image was very broad. And I think then one wants to ask about nuclear detonations, given the possible variation between one asteroid and another. How confident do you expect we'll be about the effect and whether the change in orbit will do what we want or maybe cause a problem?
Right. Great question. So prior to DART, there had been a lot of simulations run, very large number. And as I said before, when you boiled all that down, it basically showed that we expected, most of the simulations were saying beta would be somewhere between a little bit more than 1 and maybe up to about 6. And so we kind of wound up, our nominal estimates sort of wound up kind of in the middle of that spread, which is a pretty good result. So I think the best way to answer the question that you raised is to and we're actively doing this now, and one of the other Nature papers speaks to this. Actually, we're planning even more publications that are going to dive into this more, is sort of reconciling the models with the data collected to the extent that we can. When Hera comes, we'll get even more close-up information that we can feed into that. And by iteratively refining these models and doing more tests, we'll build that confidence that we will get the effect that we expect and that it will affect the orbit the way that we expect and so on.
How much does the chemical composition of the asteroid affect that beta number? Are you expecting different asteroid types to produce different beta numbers?
It's a good question. The chemistry of the material itself is not necessarily quite so much the issue, but the relationship between the material chemistry and the broader morphology of the object is important. So for instance, take Bennu. The OSIRIS-REx mission targets a carbonaceous asteroid, has a density of like 1.3 grams per cubic centimeter, bulk density. Very carbonaceous, dark, low albedo. Take the Hayabusa 2 target, Ryugu, about twice the size of Bennu, but almost the same spectral type. Not exactly the same, but it is carbonaceous, very dark, very low albedo, almost exactly identical bulk density. And so what that tells us is that the macro porosity of those objects is roughly 50%. Now take an object like Itokawa, which is S-class. It's more silicaceous than carbonaceous, which is similar to Didymos. So see, that bulk density there is more like 1.9 grams per cubic centimeter, something close to 2. And we think, as I showed you there, that for Didymos and Dimorphos, the bulk density is something maybe like 2 to 2.5 grams per cubic centimeter. And so it may be that the porosity, the macro porosity of objects in that taxonomic class tends to be different than the C types. And that could very well change the beta, the characteristic beta that you would expect between them. But it's more of a structural effect than a chemical effect. The chemical effect is the signature. You can think of it that way.
Let's thank Brent Barbie again. So our next and final speaker is David Koplow, and he's going to be talking about the nuclear option for planetary defense, some legal impediments. David Koplow is a professor of law at Georgetown, and he's been working on topics like this and on arms control for many years.
So I hope at this point you're ready now for something completely different. Here at the end of the day, they finally give the microphone to the lawyer. And my job is to give you the bad news about the legal and policy constraints that may inhibit undertaking some of the operations that you very sensibly and very earnestly want to undertake in planetary defense. And my format for doing this will be to offer you a miniature law school education. And I do this with some trepidation because I know all of you decided some time ago not to pursue a legal education. So I will try to be gentle. I will not use the Socratic method. I will not charge you tuition. I will not administer a final exam. What I will try to do is some treaty interpretation and show you the legal texts that are relevant here and how lawyers think about and try to manipulate those doctrines. And I also have to note that as a lawyer, my slides are entirely text. I'm going to show you the words of the treaties. And unlike our previous speakers who were able to offer you beautiful pictures, I'm having a little bit of PowerPoint envy here and only showing you text. And this kind of interdisciplinary work is always interesting and rewarding, even though it does set up like an old joke. I don't have a punchline for that line at the start, but maybe some of you do, and we can talk about that during the question and answer session. As an institutional matter, you're probably familiar with the Chief NASA office responsible for planetary defense, the Planetary Defense Coordination Office, and the international structure within which NASA and the companion space agencies from other countries have assembled to try to begin work on the mission to intercept a dangerous incoming asteroid, the Space Mission Planning Advisory Group, known as SamePage. And some time ago, some years ago, SamePage determined that although, of course, planetary defense is 99.99999% an issue of science and technology, there are nonetheless some important and unresolved legal issues as well. So SamePage chartered an international group of international lawyers to advise them about the legal aspects, and I was privileged to represent NASA on the work of that international group. And you can see our report on the SamePage website, administered by the European Space Agency, if you're interested. What I'd like to talk with you about today is two problems and one partial solution. The first set of problems comes up with the special aspect of a potential planetary defense mission that might use a nuclear explosive. And there are three treaties, or in one case, a collection of treaties that are relevant to that particular kind of mission. The second kind of issue is about liability, financial and legal liability, for any kind of a planetary mission, whether it uses a nuclear explosive or anything else. The general question of what happens if something goes wrong in the planetary defense mission. And then finally talk a little bit about some potential solutions, and it will not surprise you that the lawyer has relatively less to say about the good news part of this. So the first treaty to talk about, this is within the context of specifically a nuclear mission, which, and of course, nuclear weapon would be nobody's first choice in a planetary defense mission. But as Brent described, if the asteroid is large and the time is short, a nuclear explosive might be the most effective mechanism for depositing a large amount of energy on the asteroid, so it belongs on the list of possible considerations. And there are three treaties that are relevant that would inhibit some of that activity. The first of them is probably the treaty that's most familiar to you. That is the Outer Space Treaty, dating from 1967, joined by almost all the spacefaring countries. It sets out the fundamental principles, the legal infrastructure for all human activities in outer space. That treaty lays out many of the foundational points. It has one article, Article 4, that's relevant to military activities. And what we're going to do in today's class is parse one sentence of Article 4 that says the parties undertake not to place in orbit around the Earth any object carrying nuclear weapons or other kinds of weapons of mass destruction. We're going to talk about nuclear, not other WMD. Install such weapons on celestial bodies or station weapons in space in any other manner. Sometimes people overestimate what this treaty, this passage actually does. They think of it as a comprehensive no nukes in space provision. But if you parse the language, you realize that it is much more narrow than that. It actually limits only 3 specific activities. And therefore, if you can organize your nuclear planetary defense mission to dodge those 3 verbs, then the treaty is less relevant. And the 3 are that you cannot place in orbit around the Earth a nuclear weapon. You cannot install such weapons in outer space, on a celestial body, or you cannot station them in space in any other manner. Ideally, a text of this sort would offer definitions of what we mean by those terms. This treaty, reflecting the drafting style of 1967, is not that comprehensive. And there's been very little state practice in interpreting those terms, so we have to sort of make it up as we go along. And one other foundational question for the legal analysis is this regulates nuclear weapons. And sometimes we use the more neutral term, nuclear explosive device, which might open up the possibility that a nuclear explosive device used for a planetary defense mission might not be considered a nuclear weapon. If you can dodge the provision in that way, then Article 4 is not relevant to a nuclear planetary defense mission. And it will not surprise you that there's been some legal analysis on what counts as a weapon. Ordinarily, the term weapon connotes something used for aggressive or malicious or harmful purposes to kill people and destroy their property. And here, if you're using a nuclear explosive device for the opposite motivation, to save people and protect their property, maybe it is not a weapon. The International Lawyers Group that I mentioned debated this, and there's some debate about this in the literature. And it is a sensible, plausible interpretation to say that a nuclear weapon is a dual purpose kind of system, much like a knife. That if you use a knife to stab somebody, that's a weapon. But if you use the knife to slice an apple, we don't usually think of that as a weapon. And so maybe you could decide that the nuclear explosive used for a planetary defense mission is not a weapon. Ultimately, that lawyers group came up with the opposite interpretation and offered the idea, which I endorse, that a nuclear explosive device is inherently a weapon all the time, that the better interpretation of this treaty is, the interpretive guideline for treaties is to try to effectuate the object and purpose of the treaty. And here we assess that the object and purpose of this treaty would address all kinds of nuclear explosive devices, regardless of the intended or avowed purpose to which it was being used in a particular circumstance, that a nuclear weapon is inherently a weapon, and regardless of how it's being interpreted or used in any particular circumstance. And again, if you think back to the knife analogy, if on your flight home after this conference, you try to take a knife on board and tell the TSA officials that, no, this is not a knife because I'm just going to use it to slice my apple, don't do that. And the same sort of thing would apply here, that we've concluded that a nuclear explosive device, and it's reinforced by the view that today, the only nuclear explosive devices around are weapons. They're devices that were built and deployed into weapons. They're currently, if they were going to be used for a planetary defense mission, they would have to be withdrawn from a weapons stockpile. And we concluded it would be too simple an evasion of the treaty for a party to say, yes, we're putting nuclear explosive devices in space, but in orbit around the Earth, but don't worry, they're not aimed at you, they're only aimed at this asteroid. We didn't think that would work, so we think that a nuclear explosive device would be a weapon, and therefore the 3 things you can't do are to place it in orbit around the Earth, to install it on a celestial body, or to station it in space in any other manner. And you tell me whether a planetary defense mission could reasonably be constructed that would not do those things, whether it would be convenient, perhaps, to place the weapon in orbit initially, a transfer orbit or some other mechanism, or whether that could be avoided. The term to install it on a celestial body is also a problematic one. As Brent mentioned, one scenario would be that you detonate the device at some standoff distance. that probably would not meet the kind of criteria of installing it. But there are other scenarios that would place the nuclear explosive device on the surface, or even, I don't know how many of you watch the Hollywood disaster movies, where there the scenario is always that Bruce Willis or Robert Duvall or somebody undertakes a suicide mission to ram the nuclear explosive right into the asteroid and blow it up that way, or even drill it down a borehole and install it below there. I hope I don't need to tell you at this point that if the movie features Bruce Willis, it's probably not a documentary. So that's probably not the favored mission, but that raises the question that you'd have to design a planetary defense mission that did not install the device, whatever it did. And then even as a lawyer, I'm not sure what stationing a weapon in outer space would mean. Nothing in space is stationary. Everything is traveling at very high speed. And so the only sense in which that might make some sense is to say that an object could be stationed with respect to something else. So conceivably, if, as in the gravity tractor scenario, a spacecraft is following a parallel trajectory alongside the asteroid for some time before the nuclear explosive is detonated, maybe that's stationing it in space, especially since it says in any other manner. So these are the kinds of interpretive issues that your lawyers will ask you to undertake, and you could possibly develop a nuclear planetary defense mission that would avoid these three terms. Just make sure your lawyer is at your side when you're doing that. So that's the Outer Space Treaty. The Limited Test Ban Treaty is an even bigger impediment. This treaty goes back to 1963, and I should mention that all the treaties we're talking about today are treaties that have been joined by most relevant countries around the world. They've been in place, the treaties have been in place for a very long time. Although they were drafted with objectives very different from planetary defense in mind, they have text that is directly relevant, and these treaties are very important back here on Earth because they regulate the arms race, and they help ensure nuclear stability and security here on Earth, so they would not lightly be departed from. And the Limited Test Ban Treaty says that countries undertake to prevent, not to carry out, a nuclear weapon test explosion or any other nuclear explosion. So this treaty does not have the escape hatch that we talked about with the Outer Space Treaty, where you might be able to reinterpret a nuclear weapon as being something else. Here, it's any nuclear explosion is prohibited in the atmosphere beyond its limits, including outer space. So this is a serious problem. This is a direct prohibition against the leading kind of scenario for a nuclear planetary defense mission. Whatever you're doing, you've got a problem under the Limited Test Ban Treaty, and you got to find some way around that. The third kind of legal impediment for a nuclear planetary defense mission comes from a cluster of treaties, generally under the rubric of nuclear nonproliferation. And of those treaties, I'll mention three. The most important is the Nuclear Nonproliferation Treaty, which is perhaps the most important nuclear treaty on Earth. And it's got one sentence that we need to look at. Each of the parties undertakes not to transfer to any recipient whatsoever nuclear weapons or other nuclear explosive devices or control over such weapons. And here the scenario of concern is, suppose the planetary defense mission, unlike DART, was being undertaken by a collection of countries, some of whom could legally possess nuclear weapons under this treaty and some of whom could not. And they were going to share responsibilities for the mission in various ways. What this treaty requires is that whatever is done, you got to make sure that control over the nuclear weapon is retained by the country that is authorized under the treaty to possess them. And that might not be too much of an impediment because the countries that can possess nuclear weapons under the treaty are the United States, Russia, and China, the UK, and France. And those are the countries who would probably participate in a planetary defense mission, and you'd have to make sure that whatever happened, that they retained control over the nuclear weapon. But the problem gets worse because one of the other things you might want to do with your planetary defense mission, your nuclear planetary defense mission, is to assemble widespread even global support for the mission. You'd want to make sure, for a variety of reasons that we could talk about further, that it's not being undertaken just by one country or a small number of countries, but it's generally supported by the world, and you'd want to drum up that kind of support around the world. And some of the other non-proliferation treaties impede countries expressing support for a nuclear explosive mission. One category of these treaties is a cluster of treaties that create nuclear weapon-free zones around the world. And there are several such treaties. This is a quotation from the one about Latin America, but there's comparable provisions for the treaty for Africa and for the South Pacific and a number of others, so that many countries around the world are governed by this. And here, the provision requires countries to refrain from encouraging or authorizing, directly or indirectly, the use of a nuclear weapon. So again, there's not much experience in interpreting these provisions, but in general, this seems on its face to prevent the countries of Latin America from encouraging or authorizing any use of a nuclear weapon. So they would, and that might well inhibit them from requesting, supporting, voting in favor of a resolution endorsing the Nuclear Planetary Defense Mission at the United Nations, or in any other way encouraging that operation. And the final example, the most recent treaty, is the Treaty on the Prohibition of Nuclear Weapons. It's now got 68 parties to it, and it very directly says that each party undertakes never, under any circumstances, to assist, encourage, or induce in any way anyone to engage in an activity prohibited to them, which includes a nuclear explosion. And so that would directly prohibit these parties, these states, from endorsing the kind of concerted global activity in a planetary defense mission that used a nuclear weapon. Moving on now to a different segment of your law school education. You have all been spared the privilege of a first-year course in torts, which I don't even wish on law students, but you're familiar with the general concept that there could be financial liability for accidents or things that go wrong with missions, including especially ultra-hazardous missions like outer space operations. And therefore, the Outer Space Treaty, which we talked about earlier, and a subsidiary treaty called the Liability Convention, deal particularly with the financial responsibility if something goes wrong in outer space. And the scenario that we've got in mind here is, suppose, say, the United States undertakes a planetary defense mission using a nuclear weapon or anything else, any other kind of planetary defense mission. And suppose that that mission is what we might call partially successful. That is, you manage to deflect the trajectory somewhat, change its path, but not sufficient to have it miss the Earth entirely. In that case, the asteroid that would have hit country X if you'd done nothing now hits country Y instead. Country X, of course, is delighted by this. Country Y might be devastated, and country Y turns to Article 2 of the Liability Convention and says the launching state, which in this case would be the United States, shall be absolutely liable to pay compensation for damage. And absolute liability means, this is where you miss something by not participating in a torts class, absolute liability means you are responsible even if you did nothing wrong. Even if you behaved according to the best state of the art and you were not negligent, you were not reckless, you did nothing at fault, the best anybody could have done, you still caused that damage on Earth, and you have absolute liability to compensate everybody in country Y for everything they've lost. Potentially, that could be, depending on the scenario, that could be enormous damages. It could be you let your brain run wild to billions, trillions of dollars, and there could be multiple country Ys, all of whom would claim that because of your activity, they were damaged in a way they would not have been damaged if you'd done nothing. That potential exposure would deter many countries from undertaking any kind of a planetary defense intervention, again, using nuclear or anything else, because of the exposure if they were despite doing everything the best they could, they were only partially successful. So what are the possible remedies? What are the possible responses to this? The International Group of Lawyers addressed a number of possible recourses, none of which is very satisfactory. It is possible to change a treaty obligation. All the treaties that I've mentioned have provisions for amendment or for withdrawal from the treaty, and those could be used. Turns out, however, that for these particular treaties, the amendment and withdrawal provisions are particularly cumbersome. They cannot be done quickly. They could not be done at the last minute. They might not be the sort of recourse that would seem optimal under these kinds of emergency circumstances. There are also a variety of excuses for non-performance of a legal obligation under international law, just as under the domestic contract law in the United States or elsewhere. There are reasons why you can sometimes fail to perform a contract obligation. And in our report, we go through a number of these changed circumstances and impossibility of performance and consent and necessity. And each of those has something to be said, and under some circumstances might be relevant, but overall, they do not provide the kind of escape hatch that might be necessary for a broad planetary defense mission. Therefore, our recommendation was the third bullet here, that is going to the United Nations Security Council. And most people don't realize how much power the Security Council would have in a situation of this sort. Security Council has the power under Chapter 7 of the UN Charter to adopt a binding resolution that is superior to prior treaties and that provides a mechanism for suspending or superseding the obligations of the Liability Convention, the Outer Space Treaty, the Limited Test Ban Treaty. The Security Council would have to find that there is a threat to the peace and decide that in order to have a planetary defense mission succeed, those contrary provisions need to be suspended or modified in some way. Security Council has never done anything remotely like that for anything remotely like an incoming asteroid, but at least in principle, that's the sort of recourse that could be had if the 5 permanent members do not cast their veto. If any one of the 5, the US, Russia, China, France, and the United Kingdom, if any one of the 5 disagrees with this course of action, then our planet truly is imperiled. The final option that I put up here is something that might be on your mind, as it is on the minds of many of my law students when I present this to them, and that is to throw away the law if, in this circumstance, it seems to lead to an absurd outcome. That is the famous phrase that the US Constitution is not a suicide pact. The same is true of international law, and if some pieces of treaty parchment stand in the way of doing what's necessary to save our planet from an extinction threat, then of course we should not allow the law to intervene. However, my analysis and my professional training is that we can do better than throwing away the law. We should be able to find some sort of mechanism that enables us to do both save the planet and retain our fidelity to the rule of law, and that's what the International Lawyers Group was designed to do. So I think that's all I've got for you today. If you've got questions or comments or rebuttals or rude noises you'd like to make, I'm happy to entertain those.
David's talk is actually much shorter than the time allotted, so there's plenty of time for discussion of this talk and actually of the other 2 talks as well. So please line up to use the microphone.
That was a slide deck full of text, but I really appreciate it. It was a great presentation. I'll just start by saying, if humanity is destroyed, not because we didn't have the means, but because the lawyers couldn't agree on the verbiage of a treaty, then we deserved it. So, I mean, you're pointing out that, treaties make a problem because one country doing this on its own, this is a worldwide threat. And you said you had the international, you said this in the very last slide, international something of lawyers to explore this.
This is the International Lawyers Working Group that was set up by Same Page.
Okay. So, of the options on the last one, I mean, have there been discussions about among lawyers from different countries and governments which one they would prefer?
Yes.
Is there
and-
any consensus building so far?
And that last slide shows the sort of things that we, oops. Oh, I don't know if I can go back. There we go. I gotta say, as a lawyer, I really enjoy it when you techies have a problem with PowerPoint slides. So I'm really I'm welcoming that. This is, in short form, the last chapter of our report to Same Page, where we went through a number of the avenues and conceded that none of them is perfect, depending on the particular scenario that you have in mind, and whether you've got, as in some cases, decades of advance notice before the catastrophe, then you've got time to line up a legal response as well as a physical response. None of them is perfect, but the best answer is the Security Council. That's the one avenue that can effectively supersede the contrary provisions of the treaties. But in order to get that, you got to get past the threat of veto from the permanent members.
Let me interrupt for a second the questioning, since we have plenty of time. I'm reminded by this discussion of the law that my wife is a lawyer who is also a singer and songwriter, and she'll be performing tonight at 8 p.m. in Ballroom B, songs that she's written about science and scientists. It's very funny. It's very interesting. I recommend it to everybody. 8 p.m. tonight, Ballroom B. Let's continue with questions for David Kaplan.
And I won't sing my answers.
Thanks for that. I know that there have been at least one Mars rover that had a nuclear generator on board to avoid having to use solar power. How did that get around these issues? Is because it's not meant to explode, or?
Good. So you know that on a deep scientific level, there's no difference between nuclear power and nuclear explosions. That it's the same uranium, the same plutonium, the same kind of chain reaction. But legally, we've crafted a very important difference between a controlled chain reaction and an uncontrolled chain reaction. That's why, in general, nuclear power plants are lawful and nuclear explosions are tightly regulated. And so the same kind of restraint that differentiates in the context of the NPT, countries that cannot lawfully possess nuclear weapons can possess nuclear power plants. And the same thing happens with spacecraft.
Actually, I can make a little correction here as a physicist. Those power plants don't involve nuclear fission at all. To the extent that nuclear power is used in these deep space missions, in particular for the Galileo mission to Jupiter and the Cassini mission to Saturn, it was plutonium power packs that are simply using the radioactive decay. It's an alpha decay, so the only serious danger to Earth, contrary to suits that were filed to prevent the launch, was not at launch. It was actually on the second flyby of Earth. If they had come in too low and disintegrated in the atmosphere, they would have greatly increased the entire radioactive burden in the atmosphere. Fortunately, that didn't happen. But just for clarity, there have been nuclear reactors launched, one by the United States and 36, if I remember correctly, by the Soviet Union, into low Earth orbit. And that's a whole separate issue. But the ones that are being used for deep space so far are not nuclear reactors.
Hi. One thing that struck me from seeing the treaty as it currently stands is that it could almost be used as a pseudo weapon in itself. You took the example of where you deflect an asteroid, instead of hitting country X, it hits country Y. Well, if you know to some accuracy that it's going to hit country X and it's not you, then every other country could try to use this treaty to not do it, assuming it's not like a dinosaur killing kind. So to the question, let's assume that they're 5 years away on the limit of what we could send a nuclear mission to an asteroid that needed a nuclear solution. And we know to some accuracy that's going to hit country X. In your professional opinion, if country X was America, what would we do? And the second part, if it wasn't America, what would we do?
Well, that's above my pay grade. And so, I mean, who knows what the response might be? I expect and sincerely hope that we would do something that probably, in today's circumstances, the United States is uniquely positioned to be able to do this kind of intervention, both because of the space expertise and the nuclear expertise, and the mating the DART mission with the nuclear explosives might be the best we can do today. And I would certainly hope that the United States would volunteer to undertake this mission, whether we were immediately in the crosshairs or not. But the legal and tort liability is a serious impediment. And if I were advising the President of the United States and telling the President that if you are only partially successful, then country Y can sue the United States for several $1 trillion, that's something to make one pause.
Well, so this might have been covered in the torts class I did not take, but if you, what you're preventing is destruction of most of the Earth, and what you end up is only destroying a little bit of it, is that still, I mean, you said a comment, something like the damage that might have been done versus the damage that would have been done. So can you subtract one from the other somehow and not be liable?
Good, so that would have been a neat way to draft the treaty. But that's not what it says. And if we were going back now to imagine with more planetary defense scenarios in mind, they could have constructed a treaty that would have allowed that kind of an offset and would have said, okay, let's make a rational choice about what has the best odds of avoiding the most harm to the most people. That would have been a plausible way of doing it. It's not what they did here. Right. So then the question would be, what caused that damage? And it might be that your intervention wound up causing less damage than if you'd done nothing. But if you've caused damage to other potential plaintiffs who would not have been hurt if you did nothing, you have liability to them. And even within country X, there might be some people who would have been hurt either way. But if there are people who hurt because of your intervention, you're liable to them. And the fact that there are other people in country X who were saved because of your intervention, you don't get to subtract. At least not under the text of this treaty as it's currently written.
Yeah, I'm glad that I'm very happy to be here. My second option into going astrophysics was being a lawyer.
Well, good for
so
you.
This is the perfect session.
It's not too late.
It's too late for me. It's related to this. There's a non-negligible likelihood that a planetary defense mission would be multi-state. But here, I'm seeing the launching state. Does that mean physical launching? So the US says, like, we have the rockets, we'll launch the beautiful nuclear thing you built, and then the United States is liable then because they're a launching mission, or can you elaborate on that?
So I'm going to answer this question, and at the end of my answer, you'll wish that I hadn't, and you'll wish that you had not asked that question. Under space law, there is a category of things called a launching state. And that's a term that is defined under the treaties. And there are a variety of ways in which you can become a launching state. If the launch is done from your territory, or from your facility inside another territory, or you procured the launch, and we don't quite know what procured means, but there are a variety of ways in which you can be a launching state, and there can be multiple launching states for a single mission. And in fact, these days, when so much space activity is so expensive that it's done by a consortium of companies and countries, maybe most missions have multiple launching states, and under this, they're all liable. And there can be some mechanism under the treaty for them to share the financial responsibility, But the plaintiff can always look to the deepest pocket, which might be the United States. Aren't you glad you asked?
So first of all, thank you for the really interesting talk. So this question is kind of related to the previous one, but I know the UN sometimes conducts peacekeeping missions, even just on Earth. And all of these, as the previous question asker pointed out, refer to states. What if a mission were done by the UN under UN AGI the same way Earth-bound peacekeeping missions are done? Is the UN itself bound by all these various treaties?
Good. So again, you're gonna regret this. Treaties in general govern the activities of states and provide rights and responsibilities for states. Some treaties also provide for the opportunity for an international organization such as the United Nations to join. These treaties are all governed by states. So it might be possible for the United Nations to launch a spacecraft, currently doesn't have the facilities for doing that, and would operate through states. And a state would not be able to evade its obligations under the treaty by saying, the General Assembly told us to do this. The Security Council, however, has a special role, as I identified under Chapter 7 of the Charter. The Security Council has the ability to scramble all these legal restraints and could do something like that.
Okay, thank you.
Sure. Let me just say one other thing, because some of you might be thinking, well, so what if instead of having a country do this, we had a private actor, a corporation do this, and maybe Elon Musk could ride to the rescue. In fact, the treaties contemplate that and prohibit it. Under most international law, here's a little background that you didn't ask about, but you're going to hear anyway. Under most international law, the rights and responsibilities are inherent in the actor itself. If you are harmed by somebody in an international context, suppose you are mugged when you are in France, or you have a contract violated by somebody in Japan, or you have been defrauded by somebody in Brazil, you have a cause of action against that particular person who did the bad thing, but you ordinarily do not have a cause of action against the country. If you get mugged in Japan, you can't sue Japan. Japan is not responsible for all the bad actions done by its person. The general rule for international law. For outer space, however, the rule is different. The Outer Space Treaty establishes, this is a very remarkable provision, that says that a country is responsible for all the space activities done by its nationals, by its persons and corporations. So if you are harmed, if somebody else is harmed by Elon Musk in space, they have a claim against Elon Musk. They also have a claim against Uncle Sam, because the United States stands behind, is responsible for all the harms done in space by its private actors. Unique rule applicable only in space. So even if the United States or any other country operates through a private actor, the country is still on the hook.
Thank you.
Yeah, I have more of a practical question. So short warning times, large asteroids, this is an emergency. As we've seen in emergencies, at least in the United States, the executive can assume massive powers, whether they like it or not. So, if the president's military and scientific advisors say you have to make a decision now, are they really going to contact you? And ask with respect to you and your profession. Right. So, number 3 is your preferred scenario, but is number 4 the more practical one? So, this is obviously a limiting case, but, we're physicists, we like to talk about limiting cases.
So, who the hell knows what might happen in an emergency? But one thing that you probably know is the United States is a very intensely lawyerized society. And the president and the National Security Council do consult their lawyers on everything, no matter how great the emergency. Whether it's going after Osama bin Laden or there's a lawyer or multiple lawyers in the room at the time and giving this kind of advice. The Security Council is also available on very short notice. They can assemble tomorrow to address this kind of a problem. Not guaranteed that they would take the kind of actions that would be necessary to authorize, to suspend the operation of the treaties that jeopardized. And therefore, the president might be in a very difficult circumstance of undertaking this mission without having the release from these treaty obligations. And the lawyer is going to say, if you violate the Limited Test Ban Treaty, you have violated international law. That is not consistent with the concept of us being a society that's governed by the rule of law, that tries to enhance the rule of law around the world. What are you going to do? I think the president would do it.
So suppose in the incident, sort of where a UN Security Council meeting breaks down and a sole country decides to take action, what happens in the immediate short term where it's clear a country is probably going to violate a treaty, and what happens afterwards? How do you actually go about prosecuting a treaty internationally on something like a non-proliferation violation or something like that, or even for like liability damages?
Good. So this really is a whole semester course, what you just asked. And I got to tell you that in the first instance, international law has very limited capabilities for preempting a bad action. You know, in domestic environments, you can go to court and a court could issue an injunction or an immediate temporary restraining order that would stop the activity. It's much harder to do that internationally. We do have an international court of justice, the World Court, where somebody could sue somebody in the ICJ and request what's called the indication of provisional measures. Provisional measures are equivalent to a temporary restraining order that would have the court order somebody to stop doing something. That's very rare, and probably the ICJ would not have jurisdiction over this kind of complaint. That, because of the peculiarities of the way that court operates, probably would not be an effective venue. After the fact, once the damage has been done, the Liability Convention does have a claims mechanism that allows the aggrieved party to proceed against the country, or even to have the aggrieved individual have your country espouse your claim and pursue the acting state inside the mechanism set up by the Liability Convention, or in the ICJ or in some other venue. There's a real question about the efficacy of those mechanisms too. If plaintiff country X sues the United States for $1 trillion, they may not get satisfied. It may not be possible for them to come after the United States for $1 trillion, but that's still a serious liability for the United States to incur that kind of judgment.
Thank you.
Thank you for giving this talk. I come from a family of lawyers, so it's quite interesting to parse the language of these treaties.
You have my sympathy.
Thank you. I'm wondering, what are the legal restrictions for planning or simulating these types of missions on Earth without launching any nuclear weapons into space, if there are any?
Good. So there again, you have to look at the exact terms of the treaty, and these treaties do not, in general, regulate things like planning or simulating or doing comprehensive studies. And therefore, up to a certain level, you can proceed without legal challenge. Testing a nuclear weapon is a particular kind of problem, and the treaties on nuclear weapons have focused on testing as the key mechanism. If you were anticipating a nuclear planetary defense mission someday, you would hope you'd give it a trial before you'd actually do it, just as the DART mission was a test of how well that kinetic impactor would work. You'd want to test several times before the actual emergency. And the Limited Test Ban Treaty would absolutely prohibit that kind of nuclear test explosion in outer space. So up to a certain level, the treaties do not yet begin to bite. But at a certain stage, something like testing, they do.
Thank you.
So when we're talking about like a large object hitting maybe a small country and a scenario where there's literally nothing left of that country anymore, what legal recourse do citizens who are outside of the country at the time have when their government literally doesn't exist anymore?
That's a problem. or at least it's a potential problem. And I gotta say again, there's no state practice, no experience with dealing with anything else. There's only been one real test case of this, where some of you may know that a Soviet satellite, happened to be a nuclear-powered satellite, crashed into Canada and spread radioactive debris over a large swath of Canada that cost Canada millions and millions of dollars to clean up. And ultimately, the Soviet Union did pay. They didn't pay as much as they should have, and there was some compromise there, but the concept here was validated. In your situation, if country Y is so completely devastated that there's nobody left there, there may not be a suitable plaintiff, but sometimes there are. Sometimes there's people who have property inside country Y who happen not to be there at the time. They can sue over the damage to their property. Sometimes the people who are killed in Planet Y have heirs who could sue for the damage done to their loved ones. So there probably would be a number of potential claimants, even if the country itself was completely obliterated.
Thank you. I really enjoyed the talk.
Well, thank you.
You mentioned previously there was a legal difference between a controlled and uncontrolled nuclear process.
Right.
How rigorous is that legal definition? Could you not make an argument that a nuclear explosive device is an attempt at controlling a nuclear process to deflect or destroy an asteroid?
So this is where our two disciplines converge, and there has not been much, it's not I'm aware of, much definitive work on this. We do know that on the one hand, nuclear power plants, nuclear medicine, that's all permitted. There could be a chain reaction there that is still allowed. Nuclear explosions, weapons or tests of weapons are prohibited. Where you draw the dividing line between those, I don't think has been fully worked out, but there is a definition of, not a legal definition, there's a definition of explosion that is an uncontrolled release of energy. And I think you can get some mileage out of that.
Okay, thank you.
There's
Like
still
this is
time.
the last question.
If there's still time, I have a second question, but if we need to cut it off, I understand.
I think we should very soon.
Okay. Does anyone else have a question before I ask a second one, or? I guess I'll go ahead. Is there any statute of limitations for this liability convention? Because I'm thinking, like, if you have an n-body gravitational system, this is a chaotic system, and anything that's ever fired into space will have butterfly effects down the road, and it's possible that, like, the Cassini probe 1,000 years from now will have knocked some asteroid into some other asteroid, and something will hit Earth. Are we liable 1,000 years in the future for anything that's ever been launched?
So this is a good place to end. And there's two answers. A, we don't know. The treaty doesn't specify that. In general, in international law, there is not an automatic statute of limitations. And the effect of a statute of limitations would be to limit when you can bring a claim. You must bring a claim reasonably soon after the damage has been done, but not automatically extending a time limit between your action and when the damage is felt. I didn't quote here the other part of Article 2, but since this group is remaining, you're sort of quasi-law students already. This treaty has a remarkable tort regime. I've talked about one half of it, the damage done on Earth. The other half is what happens if the damage is done in space to somebody else's satellites. And the reason this is so complicated, so interesting, is that the tort rule for damage done in space is different. For damage done on Earth, it's absolute liability. For damage done in space, it's liability for fault, essentially for negligence. The drafters of the treaty decided to set out these two very different tort regimes. There's been one episode of testing it with respect to activities on Earth. The collisions in outer space have never been tested. And part of the reason is that although there have been collisions, they're so clear as to who's at fault when two satellites collide. And it might be that a satellite collides we think with a piece of debris that came off some other satellite. It's hard to be able to prove what caused it and who was at fault. So the point is, we don't have much practice in working through this. All we've got at this point is the text of the treaties.
Thank you so much.
So let's thank all three speakers, Steve Chesley, Brent Barbie, and David Kaplow.